Hi folks, today we're going to talk about the review for the Unit 5 Test 3 that focuses on the graphs of rational functions. For number 1 and number 2 it says find the following, but remember to write the ordered pair for any holes. So in x comma y. If there's no hole, write none. If there's no intercepts, write none. If there's no asymptotes, write none. So it's important to not leave anything blank to make it look like you didn't do something. Just write none if there isn't anything there for that particular characteristic. So for number 1, the function is f of x equals 1 over x minus 4. This looks like we've transformed the parent function 4 units to the right. So that would kind of be from yesterday's notes, but it's not something that's asked for. Now, it's pretty easy to identify the holes of the graphs. This is the factored form. There's no common factors on top and bottom to cross out, so that means that there are no holes. The vertical asymptote comes from the denominator. The denominator is x minus 4. And so if I'm trying to find the vertical asymptote, I'd set x minus 4 equal to 0, and the opposite of minus 4 is a positive 4. So that's the vertical asymptote. The domain is all real numbers except any x values that go along with the vertical asymptote or a hole. You have to take those out. So all real numbers except x can't be equal to 4 because there's a vertical asymptote where x equals 4. So no points will be on that. And there's no hole to have an x value to take out either. The horizontal asymptote is y equals something. What you look at is the degree of the numerator and the denominator. The degree of the denominator is 1. The degree of the numerator is 0 because we don't have an x that's visible. So it's like x to the power of 0, which is 1. So if the degree on the bottom is bigger, degree in denom is bigger, then what that means is the horizontal asymptote must be y equals 0, just like in the parent function. Which makes sense because we discovered here that we're shifting the parent function 4 units to the right, and when you shift to the right, the horizontal asymptote doesn't change. So it's still the same thing as the horizontal asymptote for the parent function. The range is all real numbers, except any y values that go along with an asymptote or a hole. There's no hole to take y values out. However, there is an asymptote at y equals 0. So we need to take out the y value of 0 in the range because there's an asymptote there. The x-intercept is the x value when y is 0. So you want to set your function equal to 0. In the case of rational functions, because it's a fraction, we can get away with just setting the numerator equal to 0. So if I set 1 equal to 0, well, that really doesn't make any sense. It gives me no information about an x value, and it's just plain wrong. So what that means is the x-intercept doesn't exist. There isn't one, so we put none. Which, if you're keeping along with kind of this mental picture, remember that the horizontal asymptote is along the x-axis, which makes sense. That's why we don't have an x-intercept, because there's an asymptote there. The y-intercept is the y value that occurs when x is 0. So I'm going to take 0 and substitute it everywhere that I see x. So f of 0 is equal to 1 over 0 minus 4. 0 minus 4 is negative 4. So my y value is negative 1/4. For number 2, I'm going to do the same thing. This is a different function, though. I can factor the numerator, whereas before there was nothing to factor. Here I can take out a GCF of the numerator. So I'm going to take out negative 2. That leaves me with x minus 3. If you aren't sure how to get that factored, just divide each term by what you're taking out. Negative 2x divided by negative 2 is x, and 6 divided by negative 2 is negative 3. That way when you distribute this back in, you get your binomial again. So there's the factored form of my function. There's no common factors on top and bottom to cross out, which means there are no holes. I put none. The vertical asymptote, remember, comes from the denominator. You can write it out like this. You can also just think opposites. Here the opposite of minus 4 is positive 4. Here the opposite of positive 2 is negative 2. So the vertical asymptote is x equals negative 2. And that happens to be the x value that I take out of the domain. So the domain is all real numbers except x can't be equal to negative 2. For the horizontal asymptote, I want to look at the degrees of the numerator and the denominator. So I look at the original function. The degree of the numerator is 1, and the degree of the denominator is 1. So what that means is your horizontal asymptote is made up of the ratio of the coefficients, because the degrees are the same. So y equals, the coefficient on top is a -2, the coefficient on bottom is a 1, and -2 over 1 is just -2. So there's my horizontal asymptote. The range is the set of all real numbers except the y value for the horizontal asymptote. I've got to take that out. The x-intercept, remember, is the x value when y is 0, so I want to set the function equal to 0. And in a fraction, that means I'm setting the numerator equal to 0. You can choose to use the numerator in the original form or the factored form. Both of them give you the same answer. So for this, I'm going to do inverse operations. -2x equals -6, and when I divide by -2, I get an x value of 3. So that's my x-intercept's x value. For the y-intercept, it's the y value when x is 0, so I'm going to substitute 0 everywhere I see an x. Again, you can use either form of the function, the original or this one. So when I substitute 0, I have -2 times 0 plus 6 over 0 plus 2. -2 times 0 is 0, and 0 plus 6 is 6. 0 plus 2 is 2. And 6 over 2 is 3. So 0, 3 is the y-intercept. So those were quick reviews on where to find the parts from each function and how to get those characteristics. So I'm going to move this up, going on to number 3. Number 3's function is a little more complicated looking. There's definitely some factoring that needs to happen in the numerator and the denominator. I'm going to start out with the denominator because I need to use magic numbers. I need two numbers that multiply to be 3 and add to be 4. And there's only one pair of numbers that do that. That would be a 3 and a 1. So x plus 3 and x plus 1. Those are my factors. In the numerator, it's a binomial. I notice the leading coefficient is -2, so I'm going to go ahead and factor out a GCF of -2. -2x squared divided by -2 leaves a x squared. And 2 divided by -2 leaves a -1. Still a binomial, but it has an x squared. This is a difference of 2 squares, so this can be factored. The square root of 1 is plus or minus 1, so we'll have an x plus 1 and an x minus 1 for the factors. And in the denominator, we've got that x plus 3 and x plus 1. Now I notice that in the top and the bottom we've got a common factor that can be canceled out. That common factor is x plus 1, but before I cancel it out, I'm going to write the domain. Remember that the domain is all real numbers except for any x values from the vertical asymptote or a whole. So any x values that make the denominator 0. So you need to be thinking opposites. The opposite of a positive 3 is a -3. So I'm going to take out -3 because -3 plus 3 would be 0, and that would make the function undefined. And then the opposite of plus 1 is -1. So x can't be -1 because -1 plus 1 is 0, and that would also make the function undefined. Now let's get back to this whole. We know there is one, and it occurs when this canceled out factor is equal to 0. So x plus 1 equals 0. The x value of the whole is -1, which is good. It makes sense. It matches because our domain, we took out an x value of -1. That's because there's a whole there. I'm just rewriting the simplified form of my function. In order to get the y value of the whole, you want to take the x value and substitute it and solve. So I'm going to take -1 and I'm going to put it here and here. You don't want to use the original function because if you put -1 here, then you're going to get a 0 for the denominator, and that's not what you want. That's useless. So negative 2 times negative 1 minus 1 over negative 1 plus 3. I'm just substituting negative 1 for x. When I do negative 1 minus 1, that's a negative 2. And negative 2 times negative 2 is 4. Negative 1 plus 3 is 2. And 4 divided by 2 is 2. So there's the whole. If the whole has an x value of negative 1, and that's what we took out here, then the vertical asymptote comes from the remaining factor. So if x plus 3 is 0, then x equals negative 3 is the vertical asymptote, which makes sense because that's what we took out of the domain. So all of these need to line up. And they all come from the denominator. The horizontal asymptote comes from the degrees of the numerator and denominator. It's easiest to look at the original function. The degree of the numerator is 2. The degree of the denominator is 2. They're the same. So that means that you need to create a ratio of the coefficients. The coefficient of the leading term is negative 2 on the top and 1 on the bottom. So negative 2 over 1 is negative 2. The x-intercept is the x value when y is 0. So we can set the numerator equal to 0 and we can solve. So if I have, let's see, you can use any of the formats for your functions. I'm just going to use this one because it seems like it's a little less complicated. So I'm going to set negative 2 times x minus 1 equal to 0. I'm going to solve. Actually, I'm going to use this because I took that out as a whole, but it still could give me an x-intercept. So negative 2 times x plus 1 times x minus 1 equals 0. There we go. So negative 2 can't equal to 0. When x plus 1 equals to 0, we get x equals negative 1. And when x minus 1 equals to 0, we get x equals 1. So we've already found out that when x is negative 1, there's a hole there, so I'm get to ignore this, which coincidentally, if I would have used this factored form, then I wouldn't have even gotten this as a solution. So that works out nicely. But the x value for the x-intercept can be 1. So there's my x-intercept. My y-intercept is the y value when x is 0, so I'm going to go substitute 0 for x here and here. Negative 2 times 0 minus 1 over 0 plus 3. 0 minus 1 is negative 1. Negative 2 times negative 1 is 2. 0 plus 3 is 3, so there's my y-intercept y value. And the range is all real numbers, except you have to take out the horizontal asymptote, so y can't be equal to negative 2. You also have to take out the whole. So the y value for the whole is 2. Y cannot be equal to 2. So when I graph all the pieces, the vertical asymptote is at x equals negative 3. 1, 2, 3. Here it is. The whole is at negative 1, 2. So negative 1, 2. I'm going to put a hole here. The horizontal asymptote is at y equals negative 2, so 1, 2. The intercept at 1, 0. 1, 0. The y-intercept is at 0, 2/3. So 0, I'm going to go up 1/3, 2/3. Not quite 3/3, not to the next line. And here's what my hyperbola looks like. I jumped that hole. There we go. And I need to have the same points down here. So I can do a couple things. I can either reflect these, or I can try and make a table to get some x values. So -1, 2, 3, maybe 4 and 5. So when x is -4 and -5, I need y values for them. So I'm going to go ahead and substitute -4 in place of x. So -2 times -4 minus 1 over -4 plus 3. -4 minus 1 is -5. -2 times -5 is 10. -4 plus 3 is -1. So this is -10. And then I'm going to use -5 for my x value, so I'm substituting that into my equation. -2 times -5 minus 1 over -5 plus 3. -5 minus -5 minus 1 is -6. -2 times -6 is 12. -5 plus 3 is -2, so we simplify, we get -6. So these should be 2 points that are on my graph. -4, -10. And -5, -6. There we go. Let's go to number 4. Number 4 says describe the transformation. So the original parent function has a vertical asymptote here and a horizontal asymptote here. In order to figure out the transformations, I should probably find the new asymptotes. And so I'm just going to go ahead and find all of these pieces, and then we'll talk about the transformations. So the x-intercept is where the hyperbola crosses the x-axis. That's right here. The point is 2, 0. The y-intercept is where the hyperbola crosses the y-axis. So that's right here, 0, 1. The vertical asymptote, it might be helpful to have a chain or some kind of string. So the vertical asymptote looks like it's right here. That's going through an x value of -2. So I'm going to go ahead and draw that in. The horizontal asymptote looks like it's about right there. So that's going through a y value of -1. So I'm going to draw that in. I check the hyperbola. It doesn't look like there are any open points, so there are no holes. The domain is all real numbers, except any x values for an asymptote or a hole. So that would be -2. I've got to take that out. The range is all real numbers, except for any y values for an asymptote or a hole. So there's no holes, but I've got to take -1 out. And the function, we'll write that in just a moment once we talk about the transformations. So there's a couple ways you can write it. So to describe the transformations, the intersection of the asymptotes used to be at 0, 0, but now it's over here at -2, -1. So the graph has shifted down 1. The graph has shifted 1, 2 units to the left. The hyperbola is still on the bottom left and the top right, so there's no reflections that are happening, but there is a vertical scale change. And I know that because from the intersection of the asymptotes, I should go to the right one and up one to get on my graph, but here I have to go to the right one and up 1, 2, 3, 4. So this distance right here is my A value. That implies that there is a vertical stretch by a factor of 4. So you can either use your x-intercept and your vertical asymptote to make the numerator and denominator and then make all the other pieces fit, or you could simply use your knowledge from yesterday and put the pieces from the transformation in transformation form. which is what I'm going to choose to do. So the a value is 4. That's what I'm stretching by. We have 1 over. We're shifting to the left 2, so this should be x plus 2. And then we're shifting down 1, so this should be minus 1. So we described the transformations, and we were able to write the function. Number 5 says write the equation of the rational function, state the characteristics of each function. So the parent function crosses at 0, 0. This right here is the new intersection of the asymptotes. This is -3, -4. That's the h and k value. -3, -4. The a value comes from going to the right 1 and up. So to go to the right 1, we only have to go up 1. So a equals 1, as it does in the parent function. That's good. There's no reflection because the hyperbola is on the bottom left and top right of the asymptotes. The horizontal asymptote goes through a y value of -4. The vertical asymptote goes through an x value of -3. The rational function, if I put all the pieces in the right place, is f of x equals a times 1 over x minus h, so x minus -3 is x plus 3, and then plus k, so minus 4. The domain is all real numbers, except you take out the x value for the asymptote. And the range is all real numbers, except you take out the y value for the asymptote. Let's go to number 6. For numbers 6 and 7, it says use the graph below to sketch problems 6 and 7. So we need to identify the asymptotes here. It looks like the vertical asymptote is going right here through an x value of 2. So x equals 2 is the vertical asymptote. The horizontal asymptote looks like it's going right here. So it's going through a y value of 1. If the graph is a little off-center, then when you look at the ends to determine where the horizontal asymptote is, the graph is going to be closer once it's kind of approached longer. So here, it hasn't approached for quite as long as it's approached over here, and so the graph over here is going to be much closer to the asymptote. So if you're kind of trying to decide between two numbers for the asymptote, I tend to look where the graph has had more time to approach it, because that gives you an idea of what it's approaching, what it's closer to. So number 6 says, using the graph above, describe the graph and the given information. So let's describe the transformation first, and then we'll talk about the asymptotes. So the transformation that happens here is we're shifting 3 units to the left. And then we're shifting 1 unit down. So the vertical asymptote used to be x equals 2. So here is x equals 2. Now shifting down 1 really doesn't do anything to the vertical asymptote, but shifting left 3 will. So 1, 2, 3. The new vertical asymptote is x going through -1. Because we've shifted that original graph to the left 3 units. And the horizontal asymptote used to be y equals 1. Shifting to the left 3, 1, 2, 3, doesn't really do anything, but shifting down 1 will. So there. The new horizontal asymptote goes through a y value of 0. So it's basically along the x-axis. So we described the transformation. Here we've given the new asymptotes. We have not actually graphed the function yet. And no, you cannot just put like a little thrown in hyperbola there. You actually have to make it look correct. So on the hyperbola here, I see a nice pretty point crossing here, and a nice pretty point here, here. I mean, you can go on and you can find more, but you want to go find the points that look like they cross at a nice place. And in order to plot those points down here with the new asymptotes, you count from the intersection of the asymptotes. So to get to this point, from the intersection of the asymptotes, you count to the right 1 and up 1, 2, 3, 4, 5, 6. So I'm going to count from here to the right 1 and up 6. To get to this point, I start at the intersection of the asymptotes. I count to the right 1, 2 and up 1, 2, 3. Starting here, I count to the right 1, 2 and up 1, 2, 3. You see how this is going? Next point here, I count to the right 1, 2, 3 and up 1, 2. So from here, 1, 2, 3, up 1, 2. And then for this one, I count to the right 1, 2, 3, 4, 5, 6 and up 1. 1, 2, 3, 4, 5, 6 and up 1. So here is the hyperbola. I do the same thing with the bottom part of the hyperbola. To get to this point, I count to the left 1 and down 1, 2, 3, 4, 5, 6. So starting here, over 1 and up 1, 2, 3, 4, 5, 6. Sorry, down, not up. Next point, starting here, count to the left 1, 2 and down 1, 2, 3. To the left 1, 2, down 1, 2, 3. And I can do it for the other points as well. But I'm going to go ahead and draw in my hyperbola here so that we can finish our review. Last problem, also connected with the original graph. It says using the graph above, describe and graph the given transformation. It's not talking about this one, it's talking about this one. This is the one we're using for problem 6 and 7. So the transformations that are occurring here, we shift to the right 4. And here we shift down 3. The vertical asymptote used to be at x equals 2. Shifting down 3, 1, 2, 3 doesn't really do anything, but shifting to the right 4 will. So 1, 2, 3, 4. That's a new vertical asymptote at x equals 6. The old horizontal asymptote was going through a y value of 1. Shifting to the right 4 doesn't really do anything, but shifting down 3, 1, 2, 3 does. So that's going through a new y value of -2. And in order to graph the hyperbola, which is the last thing that we need to do, we start from the intersection of the asymptotes, and we do the same counting that we did before to get to the points. So over 1 up 1, 2, 3, 4, 5, 6, over 2 up 3, over 3 up 2. Over 1 up 1, 2, 3, 4, 5, 6, over 2 up 3, over 3 up 2. The bottom part of the hyperbola, to the left 1 and down 6, to the left 2 and down 3, to the left 3 and down 2. To the left 1 and down 1, 2, 3, 4, 5, 6. To the left 2 and down 3. To the left 3 and down 2. There's the hyperbola, and make sure that it approaches, but it never touches. There we go. So that's the review for your test that covers graphs of rational functions. Good luck studying, and we'll see you tomorrow.